Hello everyone, this is Manas, your friend and tutor, and guys, today we'll be continuing with our discussion on Mohr circle, and this is going to be the final case, and that's two mutually direct perpendicular stress combined with shear stress. That's it. Let's begin. Here we go. So this is the element or a member which is subjected to normal tensile stress sigma x and sigma y, and there is shear stress also. Okay, top face and also in the face left and right. Let's see how things can be worked out. So the first thing that you need to do is to draw a coordinate axis like this. And by the way, this R is the origin. So all the distances, be it the tangential stress, be it the normal stress, have to be taken with respect to R. If it is towards the right of R, take it as positive. If it is towards the left, take it as negative. Similarly, if it is in a direction upwards from R, you have to take it as positive, and if it is downwards, you have to take it as negative. Here we go. So first of all, let me fix this sigma x, and this is basically a case where I'm assuming that sigma x is greater than sigma y. So sigma x is going to be somewhere here. Let's say this is sigma x. Let me just write sigma x over here. Okay, this is basically a case explaining you how to implement the concept, how to draw the Mohr circle. Here we go. And sigma y is less, so it will be somewhere here. Okay, this has been chosen randomly. With the help of a very beautiful numerical problem, we will do the entire post-mortem of calculating all the stuff, principal planes, sigma major, sigma minor, tau max, all of that and much more coming up in today's session. So if you're this way through the video, better watch it right till the end. Let's resume. So that's sigma x and that's sigma y. You need to locate the center. The center will obviously be somewhere here, isn't it? Anyway, before that, we need to fix this shear stress also. So this shear stress over here, if you just try to take a look, this is the element, and the shear stress on this face is in this direction and this direction. Try to take a look. What sort of a rotation is this? Let me erase this. What sort of a rotation is this shear force or shear stress, let's say, is going to give? It's a clockwise rotation. I already told you, if it's a clockwise rotation, shear stress has to be taken as positive, and if it is anti-clockwise, it has to be taken as negative. So we are talking about this face on which sigma x is already acting. That means this point M. So we know shear stress will be positive. That means upwards. Done. What about the sigma y? If you take a look, this is sigma y, and this appears as if this is going to be in the anti-clockwise sense here, like this, anti-clockwise sense, therefore negative. So sigma y is acting here, downwards. Okay, negative sign means downwards. There you go. That's it. And when you join this point, you'll automatically get this center. That's it. Now you've got OP and OQ. OP and OQ are these two planes. This is OP and this is OQ. Remember, two perpendicular planes. Here they've been separated by an angle of 90 degrees, but in the Mohr circle they have been separated by an angle of 180 degrees. So that's the entire idea. Okay, let's get back to business. Right? Fine. So with OP as the radius, draw a circle. That's the Mohr circle. Once it is drawn, you can calculate all the stuff very easily. Now what we need to find is the normal stress on a plane at an angle theta with the vertical in the anti-clockwise sense. So we want to find the normal stress here. This is going to be called as sigma n. We want to find the tangential stress along the plane. This is going to be known as sigma t. So first of all, you need to locate the point on the circumference of the Mohr circle. If in the configuration diagram it makes an angle theta, then in the Mohr circle it is going to be making an angle of 2 theta, always with OP. If you haven't seen my previous lectures, my recommendation to you, that go ahead and watch my lecture, only one lecture, that too, on Mohr circle. Do that. So we have to take the measurement of 2 theta with respect to OP. Okay, let me draw that. Here it is. That's 2 theta. If this is theta in the configuration diagram, in the Mohr circle it has to be made 2 theta. Okay, and that's it. That's point T. Drop a perpendicular from T onto this horizontal. The point over here which you get, let's say this is S, and join T with R. Done. Now let's say you want to find the value of sigma n. So sigma n basically is going to be equal to Rs done. Let's say you want the value of sigma t. Sigma t is going to be equal to Ts. Let's say you want the value of sigma r, that means the resultant. So resultant is going to be equal to RT, and the angle the resultant makes with the horizontal is going to be this angle TRS. Angle TRS. So this is how you can actually analyze this problem. Okay. Now let me take up a very real case. It's a numerical which I have taken, and let's try to do a complete post-mortem of that numerical. Let's see how it works out. Here we go. And this, by the way, this V and U, let me just tell you, this over here RV is the minor principal stress, and this over here is the major principal stress. Let me just write this, complete this. Okay, so major is how much, that is RU, and minor is how much, that is RV. If someone tells you what is the angle that the major and minor principal stress make with the vertical, make with OP, make with this vertical plane over here, well, the angle that these principal plane would make is this. This is going to be theta P2, and by the way, this is going to be theta P1. You can also do the measurement in the clockwise sense also, no issues, but you need to specify that very clearly. Okay, so that was all about how you can analyze stuff. Now let me take a real case. Let me take up a problem and let's see what happens. Okay, let us just try to read that entire description. The stresses on two perpendicular planes through a point in a body are 30 MPa and 15 MPa. Okay, these are two perpendicular stresses. Okay, or stresses on two perpendicular planes. So let me have the element. So number one, we have this 30 MPa. Let me fix that. Number two, we have this 15 MPa on a plane perpendicular to this. That means this plane, 15 MPa. Both are tensile. That's why you see this outward. Secondly, we have this shear stress of 25 MPa. So let me just fix this one over here. Let's say if this is clockwise, then along this plane, okay, the complementary one is going to be in this direction. So one clock and one anti-clock. Okay, this over here is clock, this makes clock, and this makes and sort of anti-clockwise arrangement. Okay, the first thing that we need to work out is the normal, tangential and resultant stress at an angle 30 degrees counterclockwise, anti-clockwise, with the face on which 30 MPa acts. So this is the face on which 30 MPa acts, this vertical face. From this vertical face you need to, or from this vertical face at an angle of 30 degrees you need to make a plane, and on that plane you need to work out the normal stress, tangential stress and the resultant stress. Now this is going to be very easy for us. Let's see. So first of all, let us start by making the coordinate axis. Here we go, and this horizontal is for normal stress, the vertical is for tangential stress or tau. Okay, sometimes you also write it as sigma t, they are synonymous, don't worry. Now here what I have done is all of these values 15, 30 and 25, they are multiples of 5. So what we basically done is we have taken this 5 megapascal division. Okay, this is 5, this is 10, this is 15, 20, 25, 30 and so on. This here also 5, 10, 15, 20, 25 and so on. Remember, each division, one division is equal to or is representing a stress of 5 megapascals. Very important for us. Now first of all, let me fit this 30 megapascals. Okay, here we go. So 5, 10, 15, 20, 25, 30, done. Let me fit this 15 also. 5, 10, 15, done. So this over here is 15, this is 30. Okay, now watch, same stuff. So that's the element on this 30 megapascal. This is the face on which this 30 megapascal stress is acting, and here this shear stress is also acting in this direction and in this direction also. Here also we have 30 megapascal, here also we have 30 megapascal, but the shear stress acting is this much, that is 25. Now this is trying to make a clockwise rotation, and therefore from M you need to move in the upward direction, positive. How much? Well, the value is 25. So 5 divisions, 5, 10, 15, 20, 25. Here we go. That's the match. Okay, done. Similarly, if you watch, let me again make a figure. In this, for sigma y, here we go. Here the arrangement is slightly different, this direction and this direction, sort of making an anti-clockwise arrangement, therefore negative. So you need to go downwards. How much? Again the same, that is 25. Okay, now join this point with this point, and somewhere its intersection is going to give you the location of the center of Mohr circle. That is the center of Mohr circle. And now with that's it. With O, let's say this is P over here, better to write this P, and this is Q. So what we've basically done is that with OP or OQ as the radius and with O as the center, we have drawn this circle, and this circle, by the way, is your Mohr circle. Now everything will become very easy. The first thing that we need to work out is, at an angle of 30 degree, we have a plane, and somewhere along this plane we need to find the value of sigma n and sigma t as well as sigma r, which by the way is the resultant. How can that be achieved? So if there is theta in this configuration diagram, that same can be represented here, or that same plane can be represented in the Mohr circle by an angle of 2 theta. So this has been given as 30 degrees, it will become 60 degrees, always with respect to OP. So that's it. This angle right here is going to be equal to 60 degrees. Okay, and it's better that I use this convention. Let me just write this as 2 theta. We've got this point. This point is known as T, always point T on the periphery. Drop a perpendicular from T onto this horizontal. Well, this is going to give rise to another point. Let's say this is S. Done. Join T with R, that is going to give you the resultant. Okay, now the first thing which we need to work out is the normal stress. So let me just tell you what that is. Let's say is done. Sigma n. Sigma n is equal to this much. This is for sigma. This is sigma n. How much? Rs. Rs. And if you just see, this is slightly less than 5, and this will probably work out as, or precisely work out as 4.6 megapascals. Okay, try to solve this on a graph paper. Done. What about sigma t? Now sigma t is this much, that is Ts, and Ts, if you just try to measure it roughly, this is 5, 10, 15, 20, slightly less than 20. Okay, and this will work out as 19 megapascals. 19 megapascals. If you want to check how much the resultant of these two stresses is, it's going to be equal to what? RT, and RT will precisely work out as 19.54 MPa. And as far as the angle that this RT makes, this angle, by the way, is represented by phi, and phi is going to be equal to what? Angle TRS, and this is going to work out as 76 degrees. So the first part of the question is done. Let's now switch over to the second part. That's very interesting. Okay, here we go. Second part, the magnitude and direction of principal stress. Okay, very interesting. So what is principal stress? Just listen to this very carefully. So there are first of all principal planes on which we get principal stress. So we get a major principal stress, we also get a minor principal stress, a maximum value of stress and a minimum value. Both of them are normal stresses or normal principal stresses. Now, what is the condition of getting these planes or reaching these planes? The principal planes are such that the value of shear stress is 0 on these planes. Okay, so if you take a look at this Mohr circle, right? If you take a look at this Mohr circle, the value of shear stress is 0 at this point. The value of shear stress is also 0 at this point. Better to change the color back to red. This point shear stress is 0, and this point also shear stress is 0. So if you want to find the magnitude of shear stress, that can be worked out very easily. Not magnitude of shear stress, but magnitude of major principal stress, that is going to be equal to RU. And if you try to make a measurement, just a rough estimate, 5, 10, 15, 20, 25, 30, 35, 40, 45 and 50, very close to 50, just before 50. This is going to be equal to 48.6. I have got the exact values as I initially made this on AutoCAD. So machine can never go wrong. Okay, that's MPa, megapascals, always. Secondly, minor principal stress. minor. Just check this out. This over here from R always has to be measured from R. VR that you see, okay, represents the minor principal stress. It's even less than 5 megapascals, okay, and it's going to be equal to 3.6 MPa. So what are we interested in right now? We are also interested in locating the position of principal planes. One is going to be theta P1, okay, on which there is going to be a principal stress, and again where there is going to be another principal plane and there is going to be another principal stress, one major and one minor. Just take a careful look. With respect to OP, always try to make measurements with respect to OP. Okay, that's the first. Okay, let's say this is for minor. Okay, now any angle, whatever angle you see here is twice. It has to be halved. That means here it is 2 theta P2, which is, this is precisely going to work out as 107. This is slightly more than 90 now. This is going to be 107 degrees. And as far as this is concerned, if you just try to calculate this, theta P2 will be equal to how much? 53.5. Yeah, this is going to work out as 53.5 degrees. Secondly, another principal plane is here. This is the location. Okay, so with respect to OP in the anti-clockwise sense always, because here also initially we made the anti-clockwise sense measurement and we took that as positive. If we go for clockwise measurement, we will take it as negative. That can also be done. I'll show you. Secondly, we've got this theta P1. So this is not theta P1, but initially it is going to be 2 theta P1. Let me just show you with respect to OP. That's it. How much is this angle? This angle, guys, this is going to be equal to 287 degrees. If we just try to work out the value of theta P1, well, that is going to work out as 143.5. 143.5 degrees. Okay. And you can clearly see that there is a difference of how much? 90 degrees. 143.5 minus 53.5 will give you 90 degrees. Always. Principal planes are separated by 90 degrees, and also shear planes or plane of maximum shear, they are also separated by 90 degrees. Now, this is working out as 143 and this is working out as 53.5. So, where exactly are these planes acting? Okay guys, now let us try to fix these two angles and let me just show you where exactly major principal stress is acting and where minor principal stress is acting. So, let me just show that to you. This is going to be theta P1. We have already seen initially that we took the angle measurement with respect to the vertical, okay, and in the anti-clockwise sense, right? Same thing. So this angle is 143.5. So that is going to be theta P1 for you, and across this plane, this major sigma major is acting. Okay, that is going to be sigma major. Secondly, if you watch, let me just extend this. Okay, with respect to the vertical, this was one plane and this is another plane. This was also with respect to the vertical. This angle over here is theta P2 and this is the plane in which minor principal stress is acting, and this is going to be sigma minor. So this is exactly how you can represent this, right? And you can clearly see that these two are separated by an angle of how much? 90 degrees. And now remember one more thing, that these two angles, right, have been measured anti-clockwise with respect to plane of sigma x is equal to 38 megapascal. That means this vertical over here. That's it. Now, in the same manner, we can work this out also, the planes of maximum shear stress. Let's see how that works out. Here we go. Planes of maximum shear stress. Okay. So this over here represents the maximum value of shear stress. This is the maximum shear stress, tau max, let's say. And here also, even if I can extend this, somewhere here also we will have the maximum shear stress. This is going to be, this is the complementary one, you can say, okay, in the negative sense. Anyway, so there is one plane OJ and there is another plane OK. Okay, so the first angle is this, the second angle is this. Done. So 2 theta S1, the angle that you are going to get over here is twice. In the configuration diagram, it has to be halved. So that's why I'm writing this as 2 theta S1. If you try to measure this up, this is going to work out as 17 degrees. Okay, now this becomes very simple. So the position of first shear plane on this configuration diagram will be equal to how much? That is going to be equal to half of that. This is 8.5 degrees. Okay. Secondly, 2 theta S2. Now that is this over here between these 2 points. That's 2 theta S2. You can also do the measurement in the clockwise sense also, right? So then put up negative sign and also specify. So 2 theta S2 will work out as, let me check, this is going to be 197 degrees. So if you just do half of that, you will get the exact value, and that will work out as 98.5. Again, the same argument, these have been measured anti-clockwise with respect to this plane, okay, or the plane on which this 30 MPa is acting. Okay guys, now try to watch this. This is the plane of maximum shear stress. So one angle over here is 98.5, always with respect to this vertical, okay. So this is slightly more, 98.5. So let us say this is theta S2. Another plane is going to be this one, this over here. And always the measurement has to be done with respect to the vertical. This over here is going to be a very small angle. This angle is 8.5, that is theta S1. So that's theta S2 and that's theta S1. And you can clearly work out the difference. They are separated by an angle of 90 degrees. 90 degrees. Okay. So these are the planes of maximum shear. Don't go anywhere. There is something else which I need to tell you. Now this theta S2, okay, it worked out as 98.5. Always measurements are in the Mohr circle, measurements are done with respect to OP, and this OP is nothing but this vertical face over here, right? So with respect to the vertical, okay, let's say this is 0 degrees. In the anti-clockwise sense, we have to mark this angle 98.5. So this over here, slightly more than 90. This is theta S2. And similarly, this is one plane and this is another plane of maximum shear. Very small angle, very small acute angle this is. Let me just do this properly. Okay, this is an extremely small angle, theta, what shall I say? Theta S1. Okay, now let's try to see where is theta S2 acting and where is theta S1 acting. Theta S1 is this OJ. For OJ we have this positive value of tau. Positive value of tau, you are going to have a clockwise shear. Okay, like this, or you can say this way also. This is also clockwise. Done. This is also clockwise. So which plane are we talking about? Theta S1. It is this plane. This plane. Okay. So it's going to be something like this. In this direction and in this direction. Okay. That's tau max. That's tau max. Okay. When you talk about this okay, this is negative value of tau. And this corresponds to OS2. Yes, 98.5. This plane. Okay, so if it is negative, then it has to be anti-clockwise. That means it is going to be in this direction, this way. Okay, so one active, other one is complementary. So that's all I wanted to explain. Let's get back to business. Final case. The normal and shearing stress on the planes of maximum shear stress. So watch this. The normal and shearing stress on the planes of maximum shear stress. So this is the plane OJ and this is the plane OK. These are the planes of maximum shear stress. Along this plane, you need to find the value of normal stress. This is fairly simple. Any measurement of normal stress has to be done with respect to R. So if you want to find the value of normal stress across this plane OJ, so sigma n obviously is going to be equal to what? RO. And this RO will work out as 22.5 megapascal. You can even count this 5, 10, 15, 20, 20 and 25 in between them. This is okay. Secondly, you want the maximum value of shear stress. Well, that is also very easy. There you go. That's the maximum value. Something like this. 5, 10, 15, 20, 25 and slightly more than 25. Okay. This is precisely going to work out as 26.1 megapascals. So guys, that was all for today. In the next video, we'll be solving objective problems from Mohr circle with the help of all these beautiful animations, and those problems are going to be taken from previous years. All the questions right from 1989 which had appeared in the gate examination on this very topic of Mohr circle will be covered up in one single video. Okay, that's a promise. So that's all for today. I'll see you again in the next video. Until then, take care, have a nice day, keep learning and keep watching. Thanks.